Hi everyone, my name is Sashya Chaudhary and I'll be presenting my second lab report, The Motion of a Falling Object. The purpose of this lab was to observe the motion of an object, in my case a ball of chapstick, dropped from rest. The goal is to observe motion of the object when the net force is non-zero, and to compare three scenarios: the object's experimental data compared to the computational model factoring only the effect of gravity, compared to a computational model factoring both gravity and turbulent drag force. The main result of this experiment was that when the three models were plotted against each other, it was seen that the computational model, factoring in only gravity, overpredicted the object's motion compared to the experimental model. However, the computational model factoring in both gravity and drag fit the experimental model better than the model without drag. And even though the fit was not perfect, I will elaborate on these discrepancies in a bit. So in the previous lab, we looked at Newton's second law, with net forces of zero, where the final velocity equaled the initial velocity. However, this time we have two forces adding up to be the net force, giving a non-zero net force, and therefore a non-constant velocity. Let's look at the weight force, which is the force that pulls the object towards the ground, or Earth, and its mass times gravitational acceleration, which is 9.8 meters per second square, times j hat, which is just the direction in which the object falls. Since the object is in free fall and falls downward, the negative sign is placed in the equation. Now, the other type of force present here is the turbulent drag force. The drag force is the force that pulls the object away from the Earth and is caused by air resistance. As the object falls, the air beneath it pushes on it and slows it down. So the faster the object is moving, the more the drag force. For this lab, we were asked to use turbulent drag, in which the object's magnitude is proportional to the square of its velocity. The formula is as shown. And B is the drag coefficient. The drag coefficient is directly related to the surface area of the object, so the more the surface area, the more the drag. Now let's take a look at Tracker. So my system was a ball of chapstick which fell in the negative y direction. I had to tilt my axis to a certain angle to model the line of my object's motion. From Tracker, I obtained my initial position, final y position, and total time, which I used later in VPython to create my computational models. On Tracker, I also calibrated the height from where the object was dropped and specified certain time frames to observe its motion. Here's a run of it. So here's where I got my data from, and this is what the graph looks like on Tracker. Now, let's take a look at my code for my computational models. So here's the code showing both. This is a computational model for both drag and gravity being factored into it. So here, the drag coefficient is 0.006. However, for the gravity model, the drag coefficient was considered to be 0. That's the main difference between the two, and of course there's no drag force formula here present in that model. For this model, the F net is equal to weight force plus drag force, and here's a run of this model. We also use arrows here. So the yellow arrow represents the weight force, while the red arrow represents drag force. And here we see that the value here is negative 1.219, which is the final position obtained from our observed data in Tracker, which means my drag coefficient should be correct. Now, here's a graph comparing all the three models. The purple line with the points represents experimental data, while the red line represents the model with only weight force, and the orange line represents the model with both weight and drag force. The model without drag overpredicts the object's motion by a large margin, meaning that the object falls faster without drag. However, at these points, the model with drag underpredicts the object's actual motion, and this may have occurred because of human error on my part, or inaccurate height and mass measurements. Now, to go back and answer a few questions. So, was there a terminal velocity? Yes, because as I will show you in a second, the lines and the graphs, certain parts of the lines were linear, and terminal velocity occurs when the weight force and drag force cancel each other out, giving a net force of 0. or a terminal velocity. So as you can see, back in these graphs, here are the points where it flattens out, or basically the lines are linear, and so there was a terminal velocity there. Now to answer the next question, what would happen to the terminal velocity if the ball was thrown rather than dropped? So the terminal velocity would remain the same, because when I will run the model for you, the graphs of the two models, one with velocity of 0 and the other with a different velocity of non-zero value, end up being the same, which is right here. So here we have the velocity as 0. Right here, you can see the ball velocity 0, and I'll run this. This provides a graph that looks like this. However, changing this velocity to, say, -10 would give me the same graph. And so, the terminal velocity remains the same. Thank you.